Awesome. Let's give this a try. Cool. Well, thank you very much for having me. I am Kathryn Berger. I'm a data scientist at the Department of Innovation, Science and Technology. And I'm really honored to be here and to kick off the keynote for FOSS4G here. So what I'm going to do is right now is such a remarkable time to be working in the geospatial sector. What I'm want to do is walk you through the evolution of how we got here and showcase what kind of amazing advances we can do in the future. I'm going to do this all within the lens of the geospatial, geohealth and environmental sciences sectors, which is where I've spent the majority of my career for the last, well, over 15 years. So without further ado, I'll get started. But first, I'm going to start with a personal story. And this is how I really got into the field to begin with. And that all starts with the woman, I guess, on your, well, I won't even give you left, right. The astronaut. Her name's Krista McAuliffe. She was meant to be the first astronaut, first teacher into space. And she was from my home state of New Hampshire, on the other side of the pond. And when the Challenger disaster happened, she never got to really fulfill her life's dream of engaging students and sparking interest in studying the planet from space. And at that time, shortly thereafterwards, NASA scientists and some of her former colleagues, teachers within the state of New Hampshire, got together and started a program called Forest Watch, which is a remarkable program. It's almost like citizen science, but for schools. And students are engaging in measuring they were studying health of trees, essentially monitoring for air pollution and ozone damage. And so each of these schools were taking tree measurements, looking at pine needles under microscopes, and taking Landsat images and doing image processing. I mean, this is a program for primary and secondary age children. So as a child in the 90s, I went to primary, secondary school throughout the 90s. This was my exposure to it, which, really sparked my interest into the field. And so when I say Landsat images, this was pre-2008, which I'll get to later. But those were not free, so that's why you see the educational image subsets. These were for all of the schools within the state of New Hampshire to access. We were using open source image processing, multi-spec, to evaluate the images, Landsat images for tree health, because as you'll know, the spectral signature of tree health decline will show in the image, or infrared, before you can see it with your own eyes. So this was, we got to go outside from our classrooms, we got to spend time outside. It was great, learning geometry on tree height. I loved it, so that really sparked my interest. I talk about Landsat. We just look quickly at the evolution of remote sensing over time. You've got 1957, Sputnik, first satellite into orbit. I mentioned Landsat in 1972, MODIS 1999, Sentinel 2014, and there's a plethora. This is not fully inclusive of all satellites. There's a plethora of ones afterwards, but I mark a line in the dotted line is really 2008 when USGS changed their policy of making Landsat images free and open, all archived, and new images must be freely available. And that was really a game changer, because it meant researchers were no longer limited by what they could afford, but essentially by computing power. So it was, there was a world of opportunities after that. And so that was pretty much remarkable. And then after that, MODIS being available, Sentinel 1 and 2 images being available for free as well. That's really opened up the doors for opportunity. And if you look at just now in 2025, we're launching, for better or worse, more spacecraft than ever. So there's more sensors out there, there's more data coming in, which is really, truly remarkable. But it's not just the freely available satellite data that is really promoting this acceleration of work. It's the open source software, it's QGIS is coming out, that's been released, that was released in 2009, and that really democratized access to the software itself. Right? So before it was limited to those that could, pay the licensing costs of private software. Now there was an opportunity where folks could undertake complex research projects without those licensing costs. Then you've got cloud-native platforms, Google Earth Engine, that emerged in 2010, Sentinel Hub 2016, Microsoft Planetary Computer in 2020. And these were serverless, scalable and they were allowed access to non-specialists. So you didn't need to know how to code, you didn't need to know much more of the nuances. You could get access, you could explore more, and that really opened up a lot of opportunities. And I touched about the open data infrastructure and data sets, but I'll talk about that a little bit more. And in the world of the geohealth, I give an example. You've got on what now being able to access freely available MODIS data. You could now go through archives of MODIS data, understand trends in between data sets within satellite data, within weather data, within ground truth measurements. And in my field of geospatial health, you could understand how those climatic conditions for one vector-borne disease could be mapped, and under climate change scenarios, you could see where they could spread. And so I showcased this example, and this was, the kind of research that was available. And this is 2011, and at the same time, that's around the same time I was finishing my PhD on looking at similar things, exploring a plethora of the MODIS data, understanding patterns for matching Lyme disease tick habitat with environmental conditions, and kind of predicting risk in that area. So you can see just in a short period of time the kind of developments in that field. Not to mention I'd gone from Forest Watch studying in the backyards of the classrooms to then getting hooked in the field. But it's not just the satellite data, it's the derived data sets that you can get from this. And I mentioned WorldPop. It's an open source demographic data set produced by Professor Andrew Tatum's team at the University of Southampton, and this is a fantastic data set, really integrating a variety of geospatial inputs, whether it's satellite data, census data, survey data, even mobile phone data, among other sources, and really pulling that together to create a population demographic data set. And that's particularly valuable when a lot of the census data is either outdated or incomplete. And the fantastic part about this is that it's open sourced, right? You can investigate, you can understand, and go through the methodologies. It's all available on GitHub. And it's these kind of data sets that then enable other layers of research. So this leads into some of the postdoctoral work that I focused on in looking at the geographic variation of zoonotic spillover of pre-pandemic events. This was 2014, so a little bit precursor before COVID, so we never got to that. But you could take those layers of information to kind of really piece them together and understand a better global picture. So it's not just the satellite data, it's not just the derived data sets that come from the satellite data, it's also those platforms enabling folks to really investigate the data sets. And I showcase here just a collaboration. During my time, I previously worked at Development Seed, a company that focuses on generating open source tools in the geospatial field. And this was a collaboration that we did with NASA's impact team in enabling their visualization, exploration, and data analysis, or VEDA dashboard, so that they could share earth science information more easily, allow everybody to access it. And this is all following open source standards and really making it, enabling folks to access it more easily. But I've gone through all of that, and right now I lead into the most exciting part of the time. And that's really with all the advances in being able to access more satellite data, more tools. We're now, with increasing compute resources, able to do a lot more in terms of the modeling. So it's not just the statistical models, we're now getting into deep learning methods. So I showcase a few of these here, whether it's multi-layer perceptrons or convolutional neural networks, being able to, for example, map flood susceptibility, looking at a number of risk factors. We then have visual transformers. So if you think about that, it really utilizes the attention mechanism, enabling the model to capture long-range dependencies and contextual information across the image. And if you think of an example of that, think building footprint extraction from remotely sensed images. You've got generative AI models, and these is more of a subfield designed to generate new data from, based on the distribution of a given data subset. And that, for example, might be more of cloud removal. So you have to understand what's underneath. Once you remove the cloud, what is underneath that image, underneath the cloud in that image. And lastly, I touch on foundational models. So think about ChatGPT. These are coming in just recent years. Models that are learning from vast amounts of data to provide a more general understanding of geospatial patterns. And if you think about foundational models in the geospatial context, that has a little bit more nuance, more complexity, because you've got the multimodal issue. You've got a number of sensors that you've got to bring into that foundational model. And I just showcase one of the examples of an open source foundational model developed by my colleagues at Development Seed, where that is, the methods are fully transparent, it's open source, you can investigate what the model's training on. And that's focused on the models for, a geospatial model for Earth. But all of that is not to say it's not without its risk. So this is a really exciting time to be in the field, but there's also things we need to keep out for. I showcase this. It's a drone image. It's just an example. It's one drone image and two different examples of delineation. The image with the, I'm going to not switch up my left and right, but the image with the white boxes, those are folks that, this is an area in Tanzania. These are local community members that have delimited the maps of the buildings within that particular area. The image with the yellow boxes, that is a modeled output. So that's a modeled output shared a few years ago from a larger software engineering company, and that's the modeled predicted footprint of the buildings in that area. And you'll notice that there is a large area in the center that is completely missing. And that's because the model was trained on it was not familiar with all sorts of different types of building types. And so it's missing the non-formal structures in the center of the image. And you think, well, why is that a problem? That's a problem because when you are using these data sets and you're using the building footprints to, say, allocate resources or estimate populations or figure out who to evacuate in case of an emergency, you're missing an entire chunk of that population in the middle of the image. And that's a problem. So I'm rounding this out to say there is a lot of advantages. There's a lot of opportunities in this field. You've now got planet level analysis. You've got data coming in every day. You've got compute resources that allow you to do research and analyses at incredible speed. You've got democratization of these open tools, which means people can collaborate together more easily. And that collaboration is really enabling a world of opportunities. But you also have the data concerns, or the concerns and the challenges in this field. And that's the data quality. You've got bias from data-rich regions and urban-centric imagery. You've also got the algorithmic bias, so the model's trained on this biased data. And then you've got a lack of explainability or a lack of incorporation of local knowledge. And so some AI models, they may be, black boxes, and it's harder to understand what the model is trained on or how to apply it or how to explain it. Or you've got just the general gap between the local realities and what the model is saying the satellite is inferring. And then you've got, lastly, data privacy issues, or issues and ethical concerns about who's monitoring who, where, and when. So I touch on those. So really, I'm bringing this together to kind of as a call to action. So data governance and representation are really just as important as the technical challenge itself. It requires a deeper integration of co-produced knowledge, adaptive planning, and climate justice principles within the field. And how do we do this? Well, I've listed off a number of approaches. We really need to build modular, interpretable, ethically aware GeoAI tools, support annotation and field data collection standards, incorporate local information as training and validation layers, and ensure representation of that underlying training data. We need to co-produce with local knowledge and enable human-in-the-loop co-decision making, and support data sovereignty and regional model tooling. So really going back to representation being the key field. Who knows the conditions on the ground better than those who are living in it and who are most interested in seeing improvements in that area? Who knows, it might spark interest with somebody within that field, and you never know what's going to happen. And lastly, I just bring together some examples in this sector of action. So I raise humanitarian OpenStreetMap. They raise, the biggest challenges are the biases and the lack of transparency of these algorithms. So most current AI models are closed, and it's unclear on what the data model was trained, and most often built in with those biases. So their solution is to tackle it by using localized models. Don't use a general model that works everywhere with codes. Use fully open source AI models so that you can investigate and that there's transparency. And use local knowledge, so human in the loop, to validate and provide feedback. I also showcase the IFRC on some of the things that they do in order to carry out data protection impact assessments to help humanitarian organizations understand the potential impacts, negative impacts of AI tech used in humanitarian programs. And it's a process that identifies risk for the protection of individual data's privacy and the mitigation of those risks. So why is this important? Because information from different data sources can sometimes be brought together to match and ID individuals from what was initially an anonymized data set. For example, a study found that it was possible to match information to identify individuals from a list containing anonymous movie ratings of over 500,000 Netflix subscribers in the USA, uncovering their apparent political preferences and other potentially sensitive information. So you can see how that might not be so good. So lastly, I leave you with some parting thoughts: where to learn more, how to get involved. Some of the organizations I've listed here. So we've got NASA Lifelines, joining collaborators from around the world and innovating new ways to use Earth observation and remote sensing to strengthen humanitarian action. AI for Good is the UN's leading platform on AI, and there's a plethora of resources here. Online seminars, trainings, networks, documentation on AI standards is fantastic. And of course, you'll be aware of Humanitarian OpenStreetMap and Map Action. I know there'll be more talks about getting involved in that later throughout this conference, but really there's options to volunteer and to get involved. But most of all, really continue your efforts on open data, open models, and open science within the community. So thanks very much.